All right. First part of the review is going to be chapter 4. Somebody asked about problem number 3. So in problem number 3, we have the fastest bird in the world, which reaches speeds of 171 kilometers per hour. So we know that the velocity of this bird is 171 kilometers per hour. Suppose that you wish to shoot such a bird, because you're a jackass, with a .22 caliber rifle that fires a bullet with a speed of 366 meters per second. Velocity of the bullet is 366 meters per second. If you fire at the instant when the bird is 30 meters directly overhead, so you know the height of the bird, we'll call it change in y, is 30 meters. How many meters ahead of the bird must you aim the rifle? Ignore gravity in this problem. What's the first thing we should do? There's kind of two choices for what we can do first. I think people have said either draw a picture or convert everything into meters per second. Do either one first if you want. Just do the other one second. So let's convert kilometers per hour into meters per second. How do I do that? Dimensional analysis. I first need to convert kilometers into meters. So I need to get rid of kilometers, put those in the denominator to get meters up top. How do I do this conversion? 1,000 meters in 1 kilometer? It's not reverse? No? That's right. Yeah. That's a very common mistake people make. Okay? 1,000 meters in 1 kilometer, not 1,000 kilometers in 1 meter. How many seconds in an hour? So we need to convert seconds, hours. How many? 3,600 seconds in 1 hour. So our kilometers are going to cancel. Our hours, oh, did our hours cancel? Oh, got to flip it. Don't make that mistake. Do 1 hour over 3,600 seconds. That's another common mistake that people make. So then our hours cancel. And when we do this conversion, we get the velocity of the bird is going to be, what do we get? 47.5 meters per second. Okay, so we've got all of our units are in SI system. Yes? Good idea to do that at the very beginning of every problem. Then we need to draw a picture. So here I am standing on the ground. I'm a stick figure. I have a gun. There's my gun. It shoots a bullet. And the bullet's going to go forward and hopefully hit a bird that is directly above me. Here's my bird. Bird. Somebody else already shot it. So the bird's going to be flying at some velocity, right? I need to aim ahead of the bird because I need to anticipate where the bird's going to be so that when my bullet goes, it actually collides with the bird and we end up with, yeah, bloody mess. Okay? So my gun, I shoot my gun, it makes a sound. Pew pew. Yeah. Okay. This is our picture. How do we solve this problem? Split things up into X and Y components. Let's do that. So let's go ahead. Let's draw this picture a little bit better. So we have some change in Y. We know that the bird is directly overhead. And we know that my bullet's going to go and be the hypotenuse of this triangle. And we know that the bullet and the bird are both going to have to travel some change in position X. Yeah? So what do I know in the X direction? Do I know the change in X of the bird? Do I know the change in X of the bullet? No, but I do know something about the bird relative to the bullet, don't I? Yeah. Change in x of the bird is equal to the change in x of the bullet. Do I know the velocity of the bird in the x direction?
Yes.
What is it?
It is 47.5 meters.
47.5. 45.7 if you're dyslexic.
Yeah.
Do I know the velocity of the bullet in the x direction? Do I know anything about the velocity of the bullet?
It will be
366 meters per second.
I know the velocity of the bullet along the hypotenuse. Is 366 meters per second.
It will be 366 times cosine theta.
Times cosine of theta. Where's theta?
Theta is in the bottom where it shows. Like, that's theta there.
That's theta?
And A will be opposite.
So what's the
Adjacent.
change in x is the opposite side.
Sine of theta.
So v bullet is v times sine of theta. Do I know what theta is?
No.
No, I don't. Can I find theta? We'll see, maybe. All right, anything else? Do I know the acceleration going on in the x direction? How fast are things accelerating in the x direction? 0. What is the acceleration pretty much usually almost always in the x direction? 0. How's that for a vague question? Pretty much always. Okay. What other variables do we need? Hmm?
Acceleration.
For the x direction. What other things? Time. Change in time that the bird has. Do we know anything about the bird's change in time? How long it's flying?
It's gonna be the same as how long the bullet's flying.
Same as the time that the bullet flies. Okay, so we have a decent amount of information. Let's look at the y direction. What's the change in y for the bird? 0. It's just traveling in a straight line. What's the change in y for the bullet? 30. The bullet has to travel this 30 meters up so that it can hit the bird. Okay. Do we know the acceleration in the y direction?
No, because you don't account for it.
Don't account for it. We don't have to worry. Yay.
Does that mean that we write it as 0 or we just ignore it?
Just ignore it.
Okay.
Ignore acceleration in the y direction. Okay. Any other variables that we can write down? The time, change in time in the y direction. Do we know that?
Yeah, it's just t, it's the same as
Same as the x direction. Okay? So this is everything that we know. Once we have everything we know written down, what do we start doing? Shrinking things down so that we can't actually see it. And what do we write down?
some equations.
Start writing down equations. What equations do we know?
Kinematic ones.
Kinematic equations. How many of them are there? 4. And we've all memorized them, right? Because they're never going away. Ever. My favorite one, I'm going to write down my favorite one. My favorite one is change in x equals v initial times change in t plus 1/2 a times change in t squared. What's the acceleration for both the x and y directions? 0. So what happens to this whole second part? Goes away. So our change in x is always going to be equal to v initial times change in time. So change in x for the bird is going to be v initial of the bird times the change in time. change in x for the bullet is equal to v initial for the bullet in the x direction times change in time. What do I know about change in x of the bird and change in x of the bullet? This is equal to this. Yeah? So if these two are equal, what does that mean for these two? They're equal as well. So I can set those two equal. V bird times change in t equals v bullet x times change at t. Yeah? What do I know about my change in t's? They're equal. It's funny, sometimes when things are the same, you don't want to say that they're the same, so I just kind of hear the S sound in the audience. I'm like, snakes, no. Sounds like snakes. You do sound like snakes. So I don't go in the turtle lab. Yeah, there's a snake in the turtle lab. It's terrifying. Don't go in there. Stay away. Dr. Rimkus might take a selfie with you. Ah. Okay. So we know the bird is equal to v bullet in the x. What was v bird? 47.5 meters per second. What was v bullet in the x direction?
366 sine theta.
366 times sine of theta. How many unknowns do I have in that equation?
Just theta.
Just theta. So I can divide both sides by 366. And I can take, so I'll find sine theta is 47.5 over 366. How do I find theta? Inverse sine of both sides. Theta equals the inverse sine of 47.5 over 366. Plug that into your fancy dancy calculator, and what do you get?
7.45.
What are the units?
Degrees.
Degrees. So I now know what theta is. Is that what I really, really want? What was I asked to find?
How
How many meters ahead of the bird?
How many meters ahead I need to aim? So I need to find x, don't I? Go back to your original picture. We had this picture. I'm looking for x. This is the theta I just found. I also know what change in y is. If I know y and I know theta, can I find x?
yeah,
How?
you use the tangent.
So tangent of theta is the opposite side. What's the opposite side?
Delta x.
Change in x. What's the adjacent side?
That's 30 meters.
It's change in y. So I can start plugging in my numbers. Tangent of 7.45 equals x divided by 30 meters. Solve this for x. X equals 30 times tangent of 7.45. Plug that in, and you find x is 3.9 meters. So aim 3.9 meters ahead of the bird, and you'll have bird for dinner. Yeah. Oh, what was it? It's a specific type. It is. They do tell you what type of bird it is. It's a spine-tailed swift.
Does that taste good?
I have no idea. I imagine it's not very filling. Because if it's the fastest bird, it's probably pretty small.
Maybe.
Hmm?
It's a function.
A flying chicken? I don't think I'd eat a flying chicken. Chickens are scary. Okay, those are all the questions that I got on chapter 4. So this would be chapter 5, number 47. We have two heavy boxes of masses 20 kilograms and 30 kilograms that sit on a smooth, frictionless surface. The boxes are in contact, and a horizontal force of 60 newtons pushes horizontally against the smaller box. What is the acceleration of the two boxes? What is the force that the smaller box exerts on the larger box? What is the force that the larger box exerts on the smaller box? Blah. Okay, so what we need to do, we need to first draw a picture and write down everything we know. So we have these two boxes. This is what they give us in the picture. We apply a force of 60 newtons to push on the boxes. We'll label them 1 and 2. What's the mass of the first box? 20 kilograms. What's the mass of the second box? 30 kilograms. How do we know that it's not reverse? Logic. The bigger box probably weighs more. That just kind of makes sense. So this is everything that we're given. 60 newtons. What should I label that? What variable would that be? That's a force that I'm pushing with. Okay. What kind of forces do I have acting on these things? If I draw the free body diagram. Gravity. Where does gravity go? Down. So I have gravity acting on box 1. FG1. What else? Normal force. Acting perpendicular to the surface. Pretty much exactly against gravity. What other forces? Friction. The boxes are in contact on a smooth, frictionless surface. Yay! So that means that we need a person in here. Wearing the wizard hat, and this person is holding their broom. And it's a special broom. How many of you are nerds? It's the Nimbus 2000. Woo! Oh God, I'm recording this, I forgot. We'll make this a private YouTube video. What else do we have? What are the forces?
Well, on the second box.
Second box? What on the second box?
Same as the first box.
Same as the first box. Gravity? And what else?
The normal force.
Normal force. Okay. Anything else? No?
What is box
You
one
got
and box two?
the force of box 1 pushing on box 2.
Force of box 1 on box 2? Anything else?
Is there a force from box 2 to box 1?
Sure.
Do we just consider those normal forces as well? Is there contact? Or are you just saying that because there's a force of push, that's what the 2 on 1 and 1 on 2 is?
1 on 2 and 2 on 1 are just the forces in contact.
Okay.
Yeah. Okay. So you could actually think of F2 on 1 as the normal force from box 2 on box 1 and vice versa. Yeah. Okay. What do we do now? There's a trick to this one. Okay. We have a net force that's acting on these boxes, right? We're given this net force. What is the net force that's acting on them? 60 newtons. Okay. What makes up that net force? Whatever we're pushing, the mass, the net mass, times the total acceleration. Okay? Or net acceleration, if you want to call it that. Okay, can I plug anything in? Do I know the net mass? What's the net mass? 50 how the heck did you get 50 kilograms? Logic. Mass 1 plus mass 2, right? You add up the two boxes. I'm applying this total force of 60 newtons to both of these boxes. And since they're in contact with each other, we assume they're not bouncing back and forth, that they're both feeling that full 60 newtons. Those two boxes combined, the force that you apply to those masses are going to give you your total acceleration. So 60 newtons equals mass 1 plus mass 2 times a total. So 60 newtons has to be equal to 20 kilograms plus 30 kilograms times A. 60 newtons equals 50 kilograms times acceleration, divide both sides by 50. Kilograms cancel. A is equal to a number, 1.2 meters per second squared. Acceleration done. Yeah, not too bad. Now what? Now we do the next part. Oh. How do we do the next part?
You have to find F1, 2,
F of 1 on 2, and what else do we have to find?
F2 on 1.
F2 on 1. We can do some logic first. F1 on 2 and F2 on 1, how are they related to each other? Equal and opposite. How do we know that? Newton's third law. Okay, so we know F12 equals F2 on 1. Wonderful. So I'm just going to pick box number 1. And I'm going to write down everything that's happening to box number 1. Sum of forces on box 1. What forces are acting on box 1 to make it move to the right? Push force, F. What forces are acting to make it move to the left? F2 on 1. So the force that I push with to the right minus the force that it's feeling pushing it to the left. Right, the force of the second box on the first one. That has to be equal to the mass of the box. What's the mass of box 1? In variables.
Oh,
It's M1, right? Yeah. And how fast is that box accelerating? Has some acceleration. Do we know the acceleration?
yeah.
Yeah. Do we know mass 1?
Yes.
Yeah. Do we know F2 on 1? No, that's what we're looking for. Do we know F?
Yes.
Yes. So let's plug in some numbers. What is F? 60 newtons. Minus F of 2 on 1. Equals mass 1. What's mass 1? 20 kilograms. What's the acceleration? 1.2 meters per second squared. Okay. We should be able to do this algebra out. I'm not going to solve it all the way. Plug in your numbers, and what do you get? Should get 36 newtons. Yep. He's walking out in protest. He wanted me to do box 2. Any questions on this one?
I have one question.
Yes, please.
You're talking about force 1 on 2 equals force 2 on 1.
Mm-hmm.
Why isn't it negative force 2 on 1?
It should be equal and opposite.
So it should be.
Yeah. Yeah. Okay. Any other questions? That was a good one. No? Okay. What else did people want to see? People wanted to see problem number 51. So let's do problem number 51 in this chapter.
One question.
Yes, please.
When you're doing the force of push on the second box, will that be 60 newtons as well? Because pushing the first box.
Yes. All right, let's do chapter 5. This is still chapter 5, number 51. In this problem, we're trying to pull a car out of the mud. Driver stretches a rope tautly from the front end of the car to a stout tree and then pushes sideways against the rope at the midpoint. When he pushes with a force of 900 newtons, the angle between the two halves of the rope on his right and his left is 170 degrees. What is the tension under the rope in these conditions? So they give you a picture, so we can just repeat that picture. And we have this basic situation. We are pushing with some force, F push is equal to 900 newtons. We are told that this angle is 170 degrees. Okay. And we're pushing, and we have this taut rope when we push. Yep. That's all we're given, and we're asked to find what is the tension in the rope. What do I do? I have no idea. From the looks on your faces, you have no idea either. What do I do? Besides, look at my solutions and convince yourself that you understand it, even though you don't. That's what I did all through physics. Huh? I looked at the teacher's solutions and, oh, I could do that.
You're like a free body diagram.
Free body diagram?
Yeah.
Okay. What forces?
It's the F push 900.
F push.
Yeah.
What else?
And you got tension.
Tension, sure. We'll do tension in red.
You got T1 and
T1 and T2.
T2. Whatever it is.
The original Terminator and Terminator 2, Judgment Day. Okay, what do I do?
Can you tell us the length of the,
Nope.
or the, in the middle? Can we say, I wasn't sure the problems of it, can we assume it's in the exact middle?
Yes, they do tell us it's in the exact middle. We are at the midpoint. So the length of the rope that you have for T1 is the same as the length for T2. Yes?
It's the same length, wouldn't the tensions be the same length?
Yeah, sure. So T1 equals T2? Sure. How do we know that? It's your word of the day. Logic. Okay. I could bring this to the philosophy department and they could get that far. Logic. That's about all they could do though. Yes?
So maybe split the T1 and T2 into like triangles, X and Y?
Oh yeah, let's split things up into components. Anytime you have something at an angle, what do you do with it? Break it into X and Y. How many times have I said that? I have lost count. Okay, break it up into X and Y. Yeah. How do you want me to break it up? Do you want me to go over and down or down and over?
We do down and over, opposite F push.
Down and over? Sure. So we have, let's say, T1Y and T1X. And I'm just going to work with T1. Yeah, why only T1? It's the same as T2, yeah. So we only need to do one of these triangles. What else do I need to do? I have this triangle drawn, right? Shouldn't I figure out more about the triangle? Figure out the new angle. What's the new angle? 85. How did we get that? 170 divided by 2. So we have this angle is 85 degrees. Logic. I'm going to title this Logic when I post it up to YouTube. Then people are going to YouTube Logic and they're going to find this video. Oh, I'm going to get destroyed in the comments. Thank you. Let's do the y direction. So what forces do I have acting in the y direction? Sum of forces in the y direction. What forces are acting up? F push. What forces are acting down? minus T1y. What other forces are acting down?
T2Y.
T2y. How do we know T1? What are T1y and T2y? How are they related? They're equals. So can't I just do 2 times T1y? And that'll take care of all the numbers. Yes? Okay. Let's do it for the x direction as well. Sum of forces in the x direction. What forces are acting to the right? Anything? What's it say? T2x. What forces are acting to the left? T1x minus T1x. What's the total acceleration of these forces? 0. So we know T2x is equal to T1x. We just proved the thing that logic told us we already knew. Whoop-de-frickin-do. Be proud of yourselves, a philosopher could not do that. Let's come back to the y direction. What do we know about these two in the y direction? F push minus T1y equals mass times acceleration in the y direction. How fast is this thing moving in the y direction? 0. It's pulled taut, so nothing happened in the y direction. So that means that I can then say F push minus 2 times T1y is equal to 0. Any questions on that? We're good with that. Yes, a
Can
question.
you put the 2 again? What did you say about it? Or
So the 2 is because we know we have T1y acting down. We also have T2y acting down,
Okay.
right? Because we have the force from both sides. So technically there is a T2y going down. I didn't draw that in because I know T1y and T2y are equal. So I can just double T1y to take that into account. Yeah? So now we'll shrink this down. Oh, gosh. No, we won't. Go to a new screen. And we'll write down we have F push equals 2 times T1y. Yeah? We look so excited. Okay. Can I plug in any numbers?
Yeah.
Yeah? What can I plug in? What's F push? 900 newtons. Equals 2 times T1y. How should I write T1y? In terms of things that I know and things that I'm looking for. I'm looking for T. I'm looking for the tension. And what part of the triangle is Ty? Do we need to go back to the triangle? Is it the adjacent? Is the adjacent side of 85? Do I have, how many unknowns do I have in this equation? 1. I just don't know T. So I can divide both sides by 2 cosine of 85. And I'll find that T is equal to 5.16 times 10 to the 3rd newtons when you plug in all those numbers. Okay? Let's talk about chapter 6 and problem number 33. Something interesting about problem number 3, it has 2 little stars next to it. What does that mean? It means it's super hard. Philosophers would crap their pants if they had to do this. So we have 2 masses. Mass 1 equals 1.5 kilograms. Mass 2 equals 3 kilograms. They're connected by a thin string running over a massless pulley. One of the masses hangs from the string. The other mass slides on a 35-degree ramp with the coefficient of kinetic friction of mu equals 0.4. What is the acceleration of the masses? So this is chapter 6, problem number 33. Let's start by drawing our picture. That's a pretty darn good triangle. I'm impressed with myself. They give us that the angle is 35 degrees. That we have box 1 connected by a string over a massless pulley to box number 2 that just kind of hangs here. We are told mass 1 equals 1.5 kilograms. We are told mass 2 equals 3 kilograms. We are also told that there is friction, and the coefficient of kinetic friction is going to be equal to 0.4. All right. I'm going to give you some stuff. Well, we're going to talk about some stuff to get you started. What's the first thing we should do? Draw the free body diagram. Okay? What forces do we have acting here? What was that?
Which box?
Either box, any forces. Give me any forces. What forces are acting on box number 1? Gravity? I heard gravity. Where does gravity go?
Down.
Straight down. Force of gravity on box number 1. What other forces? F of n. Where does F of n go? Perpendicular to the surface. What other forces? Friction? Where does friction go?
The opposite way of the tension.
Opposite of the tension? Are you sure?
No, there's no friction, right?
There is friction. Mu k is 0.4. How do you know the box isn't sliding down the incline? Because the other box is heavier. How did we figure out that it wasn't going that way then? Logic, yay. What else? What other forces? Somebody's already said it. The tension, where does the tension go? Tension goes in this room. It's a very tense room. Tense bunch of students. Goes opposite direction. Tension. Anything else? On box number 1? No? Okay, what about box number 2?
Tension.
Tension, where does tension go? Up. Anything else? Gravity, where does gravity go? Down. Okay. Anything else going on here? Anything else that we know?
Can I ask a question?
Yes.
Why is it important that the pulley is massless?
If the pulley is not massless, then that introduces friction into the pulley, so that changes the forces T and T. Notice something, I labeled the two T's the same. Are they the same?
Yeah.
Yeah, why are they the same? Because they're connected to each other. This string isn't stretching, it's not compressing, so that string has to have the same tension throughout it, okay? So they both have the same tension. Okay, T is the same, there's only one T. That also means something else. That means something else very, very useful. How fast are these boxes accelerating? Nope, they do have some acceleration. They have some acceleration A. We'll say A1 for the first box. We'll say A2 for the second box. Yeah, they are equal. How do we know that? What happens if they weren't equal? Let's say this second box, we're accelerating slower than the first box. So the first box is going to start accelerating, it's going to start catching up to the second box, right? If the first box has a higher acceleration than the second box, it would start catching up to it. What happens to tension if your box is catching up? There's no more tension, right? So you don't have a taut string, so you don't have any tension if the accelerations aren't the same. What happens if acceleration of box number 1 is slower than box number 2? then you break the string and you have no tension. And then the problem gets really, really easy. Okay? All right. So I've given you A1 equals A2. Just call those both A. I've given you that there's only one tension. We've identified all the forces acting on every single box. What should we do with these forces on box number 1? Separate them into X and Y. So we want to move our coordinate axis so that we have some force due to gravity that's going in the Y direction. We'll call that FGY. We have some little bit that's going in the X direction along that incline. We'll call that FGX. Use all these force diagrams and write down the force equations and finish out this problem to find the acceleration of the boxes. Okay, work on this in your groups. So now, how do we actually solve all this? We need to separate things out for each box into the X and Y directions and see what we can get. Remember, we are looking for the acceleration of both of these boxes, A. So we'll shrink this down. And we'll look at each of the individual boxes. First, we'll look at box 1. And we'll see what's going on in the X direction and what's going on in the Y direction. So in the X direction, we'll write down the sum of forces in the X direction. We're going to say that tension pulling it up the incline is going to be positive, so we'll say we have tension pulling it up. And then we have force of gravity on the first box in the X direction, and we have the force of friction in the X direction pulling this box down the incline. And that's going to be equal to mass 1 times the acceleration in the X direction. I can expand these things outwards. So I get T minus FG1x is going to be FG1 times sine of 35. So it's going to be M1 times G times the sine of 35 degrees. Minus force of friction, which is going to be mu times the normal force. That's going to be equal to M1 times the acceleration in the X direction. And again, I'm going to drop that little x just because we know that everything has the exact same acceleration. So I'm looking for A, so I need to solve this whole equation for A. I can divide both sides by M1, and that will give me an equation for my acceleration. So my acceleration is going to be equal to T minus M1 times G times sine of 35 minus mu times the normal force, all divided by M1. And then I can look at the Y direction for box 1. And in the Y direction, I know that the sum of forces in the Y direction is going to be equal to the normal force acting perpendicular to the incline minus mgy, the force of gravity in the Y direction. So force of gravity in the Y direction, FGY. And that's going to have to be equal to 0 because this box isn't bouncing up and down as it goes along the incline. So the normal force is going to be equal to the force of gravity in the Y direction. And we can expand that outwards so that we get the force of gravity in the Y direction is going to be mg times the cosine of 35. We should be good at doing that by now. If we're not, you need to come in and talk to me for practice, or you need to practice these problems at home more. And we can plug this in to our normal force to find that our acceleration is T minus M1 times G times sine of 35 minus mu times M1 times G times cosine of 35. Kind of running out of a little bit of room here. And then divide all of that by M1. And if I take stock of what I know what M1 is. Let's just cross off things that I know. I know M1, I know G, I know sine of 35, I know what mu is, M1 I still know, I know G, cosine 35, I know M1. So the one thing I want to find is T. I want to find the tension. So to find this, we need to switch over to box number 2. And for box number 2, I can do the same process I did for box number 1. sum of forces in the x direction for box number 2. So I'm doing the x direction. For box number 2, there's nothing happening in the x direction. Absolutely nothing. So there's nothing I can write. For box number 2 in the y direction, I can write the sum of forces in the y direction. And I can say, let's say up is positive, so I have tension pulling this box up, minus the force of gravity on box 2, and that's going to be equal to the mass 2 times the acceleration of that box, and there's something I have to remember. I have to put on a negative. So why does that negative pop into there? Let's quickly draw a little sketch of what we have. We have this box number 2 with tension pulling it up, and we have the force of gravity pulling it down. Now what I've done here, as I said, anything going up, like the tension, is going to be positive. I did that when I wrote down my sum of force equations. I said anything moving in the direction of tension is going to be positive, which means anything moving opposite, like gravity, has to be negative. And since this box is going to be dragging everything along the incline and be dragging everything down, and I've said that gravity, Fg2, is negative, that means that the acceleration that is actually pulling everything downwards also has to be negative. So that negative right here comes in because the box is moving downwards. Okay? So I can take this and I can solve this equation for the tension. So I can find that tension, T, is equal to negative m2 times A plus Fg2, which is m2 times g. Then I can take this tension equation and I can plug it in to my acceleration equation. So my acceleration is now going to be, instead of t, I plug in negative m2 times a plus m2 times g. That's just plugging in the tension into my acceleration equation that I just found for the box number 1, minus m1 times g times sine of 35, minus mu times m1 times g times cosine of 35, and I can divide all of that by m1. And now I need to do some geometry or some algebra exercises to get everything to work out. So the first step I'm going to do, I'm going to multiply both sides by m1 to get rid of my fraction. Again, this is all prereq knowledge. We should be very good at doing algebra. And let's keep going. Let's show you how this actually works out. So I multiply both sides by m1, and that gives me the following. I get m1 times a is equal to negative m2 times a plus m2 times g minus m1 times g times sine of 35 minus mu times m1 times g times cosine of 35. I'm trying to find out what a is, so I need to get all my a's on the same side. So I need to move this m2a to the other side. To do that, I add m2a to both sides. So it's going to cancel on my right-hand side and give me m1 times a plus m2 times a on the left is going to be equal to m2 times g minus m1 times g times sine of 35 minus mu times m1 times g times cosine of 35. I can factor out my a on the left, so I factor out an a and I'm left with a times m1 plus m2 in parentheses equals m2 times g minus m1 times g times sine of 35 minus mu times m1 times g times cosine of 35. Then I divide both sides by m1 plus m2 to get my a by itself. And this will give me an equation for A that says that acceleration is equal to m2 times g minus m1 times g times sine of 35 minus mu times m1 times g times cosine of 35, all divided by m1 plus m2. And now I can just plug in my numbers. So my acceleration, when I plug in numbers, I plug in for mass 2, I have 3 kilograms times g is 9.8 meters per second squared, minus m1, which is 1.5 kilograms, times g, which is still 9.8, times sine of 35 degrees, minus my mu, which is 0.4, times m1, which is 1.5, times g, which is 9.8, times cosine of 35. All divided by m1 plus m2, which is 1.5 plus 3.0. And when you plug all of this into your calculator, you will find the acceleration is equal to 3.6 meters per second squared. And that's your final answer.